Linear probabilistic modeling is a statistical method that uses a linear function to plot a regression line from a set of data. We then use that function to evaluate current values and predict future values along the line. Y equals x is the most basic linear function that you learned in algebra, and models the linear relation between variables y and x. Y equals beta naught plus beta sub 1 times x plus the random deviation is the function used for the linear probabilistic model. Breaking down this function, beta naught is your y-intercept, beta sub 1 is your slope multiplied by x, and epsilon is the random deviation, which is the distance between a point in the dataset and the regression line. Let's take a hypothetical set of data from UCF engineering admissions. Looking at this data table over a 20-year period, in 2-year increments we can see that every 2 years the applicants increased by 3,000. And on the right, you can see how many acceptances were corresponding to each year. Modeling this function on a graph, we can see that the y-intercept is 1,000, the slope is 12, and the random deviation is modeled by the purple lines on each point. The regression line is given in red, which passes through some, but not all, of the data points. Now let's look at another hypothetical example. Let's say we have the engineer Elon Musk, who needs thousands of robots, but he's too busy with PR stunts to make them himself. He decides to order pre-made kits to his development center. When he gets them all, he lays them out on the development center floor. Pictured here are the individual sets of orders, where one black dot represents 10 robotics kits, and one red dot represents a defective kit. Modeling this data into a table, we can see that on average, for every 100 robotics kits, we are getting one defective kit, which is given by the slope of 100 times x. The y-intercept is 0, and the random deviation is shown on this graph, with the regression line plotted in red. This gives our engineer an idea of how many defective kits he would get in his next order. Some important things to note is that while these examples were clean, real-world application sees much more variability, and as an engineer, it's up to you to judge whether the application of this model would appropriately account for any safety or oversight regulations that you have on your project.